In the depths of the Pacific Northwest, a quiet yet unmistakable tension has been building beneath the slopes of Mount St. Helens. For months, subtle changes in the region have hinted at forces stirring far below the surface, signals that, to the trained eye, tell a story much older and more complex than the modern towns and forests surrounding the volcano. By early spring, the signs had become too consistent to ignore. Seismographs reported an unusual clustering of tremors, hundreds of them beneath the mountain's northern flank. Most were too small to be felt by anyone without specialized instruments, yet their sheer number was extraordinary. Over 400 individual seismic events recorded between January and March, concentrated in the same zone that catastrophically collapsed in 1980. That eruption had been one of the most infamous natural disasters in American history, claiming lives, erasing landscapes, and forever altering the mountain's profile. Now, 4 decades later, something was stirring again in that scarred region. The tremors were only part of the story. Aerial and satellite imagery began to reveal that the ground itself was changing, with subtle swelling appearing in successive measurements, an uplift so gradual it escaped the notice of casual hikers, yet impossible for scientists to overlook. This deformation, measured in centimeters but increasing week by week, often points to magma pushing upward through the crust, displacing rock and soil in its slow ascent. For volcanologists, the memory of the last time such a bulge appeared still looms large, for in 1980 it preceded an eruption of staggering force. Adding to the unease was the emerging chemical signature, suggesting even more activity within the restless mountain. The mountain's vents and fumaroles soon began to tell their own story. Volcanic gas emissions, particularly sulfur dioxide, rose sharply, tripling in concentration within just a few weeks. Alongside this surge came elevated levels of carbon dioxide and hydrogen sulfide, gases frequently associated with rising magma. When such emissions occur simultaneously with ground deformation and heightened seismic activity, the conclusion is rarely comforting. It usually means that pressure is building beneath the volcano, seeking release. Even before humans could fully interpret these changes, wildlife seemed to sense the shift. Birdsong faded into silence. Elk herds that once grazed freely at the mountain's base began to move away in growing numbers, and smaller mammals appeared restless and disoriented. Animals have long been known to detect subtle changes in atmospheric pressure or the Earth's magnetic field, and here, their behavior spoke volumes. Locals soon reported another strange sign, an uncanny, low-frequency hum that seemed to rise from deep within the earth. To the human ear it resembled the distant drone of an unseen engine, steady and unsettling. At the Cascades Volcano Observatory, scientists confirmed that this was no superstition. Sensitive instruments were detecting harmonic tremors, continuous seismic vibrations often linked to magma moving through underground fractures. While such activity alone might have suggested an isolated period of volcanic recharging, this episode was watched with unusual intensity for another reason: the possibility that Mount St. Helens was not acting alone. Geological processes rarely remain confined within human-made boundaries, and recent observations elsewhere had sparked a troubling conversation. Nearly 900 kilometers to the east, beneath the serene expanse of Yellowstone National Park, another volcanic giant appeared restless. At the Norris Geyser Basin, geothermal activity was on the rise, and Steamboat Geyser, the tallest active geyser on Earth, was erupting more frequently than usual, in a pattern some found eerily synchronized with Mount St. Helens' recent stirrings. The notion that two volcanoes separated by hundreds of miles could be connected is not one that scientists raise lightly, yet seismic arrays beneath Yellowstone Lake had recorded long-period earthquakes, deep low-frequency quakes often tied to the movement of magma or hydrothermal fluids. GPS stations had also detected measurable uplift in the Yellowstone caldera, hinting at a persistent force pushing upward from below. The idea of cascading eruptions has long been debated in volcanology, for volcanoes are not always the isolated chimneys of popular imagination. Instead, the Earth's crust is a complex patchwork of plates, faults, and conduits, where significant pressure changes in one system can influence others by redistributing tectonic stress. While direct magma transfer between distant volcanoes remains unlikely, the possibility that one restless giant might destabilize another has become an unsettling topic of scientific study. In the case of Yellowstone, a supervolcano fueled by a deep mantle plume, even small changes in regional tectonic forces could have consequences. If stress patterns were to shift as a result of magma movements beneath Mount St. Helens, they could, at least in theory, influence Yellowstone's own magmatic system. It was an unsettling but scientifically valid question. Could the rumblings beneath Mount St. Helens be part of a larger chain of events? Adding to the intrigue, satellite-based interferometric radar detected subtle surface deformations within Yellowstone, changes strikingly similar to those recorded before past volcanic episodes. These were not dramatic bulges, but broad, gentle uplifts that hinted at evolving pressure dynamics underground. Historical records showed that when such uplift coincided with an uptick in long-period earthquakes, volcanic or hydrothermal activity sometimes followed. Meanwhile, advanced computer models began simulating possible interactions between these two massive volcanic systems, drawing on seismic readings, GPS deformation patterns, and historical eruption sequences. Some scenarios suggested that even minor disturbances in one system could alter the stability of the other. While the probability of a direct triggering event remained small, it could not be dismissed entirely. As monitoring continued, the phrase cascade effect began circulating in both scientific and media discussions, not only as a nod to the Cascade Range, where Mount St. Helens resides, but also as a metaphor for a theoretical domino effect in which one volcanic event could influence another, even across vast distances. This was not mere speculation. Historical precedents existed. Following Mount Pinatubo's eruption in 1991, several volcanoes across the Philippines and neighboring regions displayed unusual seismic activity, and in Iceland, eruptions had sometimes altered pressures in nearby volcanic systems, sparking subsequent unrest. Seismic tomography studies of North America revealed deep crustal structures linking parts of the Cascades to regions farther east. While these were not open magma tunnels, they represented ancient fracture-filled pathways capable of transmitting stress over great distances. In such a scenario, a significant eruption or magmatic intrusion in one volcano could subtly adjust the equilibrium of another. For geologists, these developments demanded vigilance. Both the Pacific Northwest and Yellowstone are under constant observation, yet the convergence of signs, Mount St. Helens' surge in seismic and gas activity coinciding with Yellowstone's uplift and increased geyser eruptions, was too unusual to ignore. What might otherwise be an ordinary recharging cycle for one volcano could, under the wrong circumstances, become the spark in a larger interconnected system. For now, the mountains remain quiet on the surface. Tourists still hike Yellowstone's trails and marvel at its geothermal wonders, and clouds drift lazily over the snowy slopes of Mount St. Helens. But beneath both, pressures shift, gases rise, and magma moves unseen. A silence scientists know may not last forever. Silence in volcanic terms does not always mean safety. Sometimes it is merely the breath before the voice. The science behind the so-called cascade effect is still in its formative stages, but the evidence continues to accumulate. The Earth's crust is not the solid, unyielding barrier many imagine. Rather, it behaves like a complex puzzle of interlocking plates fractured by faults. After Mount St. Helens' catastrophic eruption in 1980, researchers noticed subtle but intriguing changes in seismic activity at other volcanoes across the Cascades. These shifts did not always lead to eruptions, yet they hinted at a level of interconnectedness that was not fully appreciated at the time. Now, with vastly improved monitoring technology, those hints are becoming clearer. Modern volcano surveillance uses a layered approach. Ground-based seismometers form the first line of detection, capable of picking up even the faintest vibrations from deep underground. Clusters of these instruments surrounding both Mount St. Helens and Yellowstone detect patterns in frequency and amplitude, helping scientists distinguish between ordinary tectonic movement and the migration of magma. Long-period earthquakes, harmonic tremors, and sudden swarms each tell a different story about what may be happening below. Gas emissions provide the second key indicator. Sulfur dioxide, carbon dioxide, and hydrogen sulfide, all common byproducts of magma movement, are carefully measured by specialized sensors on the ground and by drones, tracking fluctuations in concentration down to parts per million. A sharp rise in sulfur dioxide often signals that fresh magma has entered shallower chambers, raising the likelihood of an eruption. Thermal imaging, whether from stationary cameras or satellites, adds yet another dimension to the monitoring network, detecting surface temperature anomalies that may indicate new fissures, expanding lava domes, or intensifying geothermal activity. When combined with high-resolution satellite radar, scientists can now measure ground deformation with extraordinary precision, sometimes detecting uplift as small as a few millimeters, providing critical insight into the restless forces moving unseen below. At Yellowstone, the integration of satellite radar and GPS networks has revealed long-term patterns of uplift and subsidence unfolding over decades. These cycles are not unusual in themselves, reflecting the slow breathing of the vast magma chamber as it expands and contracts over time. What has begun to concern scientists is the rate of change and, more importantly, its apparent alignment with the unrest at Mount St. Helens. Even if any connection between the two volcanoes is indirect, the synchrony of these events is unusual enough to warrant close scrutiny. Despite the unsettling scenarios such connections imply, the probability of a direct chain reaction remains low. A far more immediate concern lies in the potential for either volcano to erupt independently, an event that could bring devastating consequences ranging from local destruction to global disruption. For Mount St. Helens, a moderate eruption could unleash lahars, fast-moving volcanic mudflows, barreling down river valleys and threatening communities, infrastructure, and ecosystems in their path. For Yellowstone, even a relatively small eruption could spread ash across vast areas, grounding flights, contaminating water supplies, and choking critical infrastructure. But what if the unimaginable happened? A full-scale Yellowstone supereruption, though highly unlikely, would dwarf any disaster in recorded history. Pyroclastic flows, searing avalanches of gas and rock, would obliterate everything within a 100-mile radius. Cities such as Bozeman and Jackson Hole would be reduced to rubble within minutes, with rescue efforts nearly impossible in the initial aftermath. Beyond the immediate devastation, ash plumes would rise into the stratosphere and spread across the globe within weeks. Sunlight would dim under a veil of fine particles, dropping average global temperatures by several degrees. This volcanic winter could persist for years, crippling agriculture, collapsing ecosystems, and triggering mass food shortages that ripple through human society. Even far smaller scenarios carry grave risks. A modest Yellowstone eruption could still eject enough ash to shut down major airports, clog machinery, poison water systems, and paralyze transportation networks. In today's interconnected world, the economic shockwaves would ripple outward almost instantly. Yet, amid these daunting possibilities, there remains reason for measured optimism. Science today is far better prepared to detect the early signs of volcanic unrest than it was decades ago. The 1980 eruption of Mount St. Helens was preceded by clear warning signs, swarms of earthquakes and bulging slopes, but at the time, our ability to